Hello everyone, my name is Yue Yi. I come from Beijing University of Posts and Telecommunications. It's my pleasure to present my poster. By using NFV technology, the Internet service providers can realize network functions in software and flexibly instantiate them in the form of virtual network functions on standard off-the-shelf servers. As for mobile edge computing, it pushes network computing and storage functions to the edge of the network to ensure the performance of delay-sensitive and computing-critical network services on resource-limited edge devices. Generally, user-customized network services are performed by service function chains, each of which is composed of a series of ordered VNFs. So, we simplify users' network service requests as SFC requests, and the elements in an SFCR are referred to VNF requests. In MEC and NFV networks, the throughput of SFCRs is an essential factor that affects the quality of experience. In this poster, we study the VNF placement problem in MEC NFV networks, aiming to maximize the number of accepted SFCRs with limited resources. First, we consider fundamental resource overheads and the sharing mechanism of VNF instances. Fundamental resource overheads are resource consumption for supporting the basic function of a VNF instance. As for shareable VNF instances, they are implemented by multi-tenancy technology, which allows one type X VNF instance to serve multiple type X VNFRs. As shown in the figure, we can assign multiple VNFRs of the same time to the same VNF instance. Even these VNFRs are from different SFCRs. In this way, we need fewer VNF instances to accomplish users' SFCRs, saving more node resources to serve more SFCRs. We formulate the throughput optimization VNF placement problem mathematically and propose a correlation-based mapping algorithm to select mapping positions for SFCRs. Moreover, we devise an adjustment algorithm to optimize the placed SFCRs, achieving a balance between node resource consumption and bandwidth consumption. We denote the substrate network as an undirected graph. Moreover, we define G gamma to indicate an SFCR gamma. We consider CPU, memory, and bandwidth constraints in formulation. We use a binary variable H gamma to indicate whether an SFCR gamma is completely mapped in the substrate network. Our target is to maximize the total number of accepted SFCRs in the network. Algorithm 1 shows the correlation-based SFCR mapping algorithm. We first construct the VNF correlation matrix for each SFCR. To reduce the number of VNF types in a node, we treat each SFCR as a whole and use cosine equation to decide which SFCR can be mapped preferentially. Based on the above mapping results, the interactive traffic between the nodes is minimized, consuming the least bandwidth resource. However, we must instantiate all kinds of VNF instances on each node, which generates a great volume of node resource consumption. Hence, we devised the adjustment algorithm. We regard the VNFRs of the same time in the same nodes as a whole, symbolized as mu. Next, for each mu in the L tempo, we select the target node from the current group. The qualified target nodes must satisfy the following conditions. The while loop will not be terminated until every mu in the group is labeled as precise. We compare our approach with the first fit and N-gain decomposition algorithm. We implement the models and algorithms based on Olivine, a widely used evaluation environment for VNF placement. The parameters used in the evaluation are listed in the table. We take CPU capacity and link capacity as variables to evaluate the performance of different solutions. The first figure shows that with the increasing CPU capacity, the throughput of our approach gradually increases from about 1,800 Mbps to 5,700 Mbps. Moreover, our approach always outperforms the benchmarks. The reason is that the benchmarks neglected the correlation between different SFRs during the mapping process, which leads to lower utilization of node resources. Similarly, in the second figure, we can see that more link capacity leads to higher network throughput. Our approach still acquires the best performance. More bandwidth resource allows our approach to adjust VNFRs more reasonably. Besides, with scarce bandwidth resources, our approach throughput is about 2,000 Mbps and 1,700 Mbps higher than that of the first fit and engine decomposition algorithms. Thank you for watching. Thank you.